So that is how you get the direction using the right hand rule. And you also see the magnitude of the torque, which we said RF sine theta, it is also equal to the parallelogram formed by these two vectors R and F. Good morning, Omar. Right, so then we ask this question, does it matter whether the order of the vectors for its direction? So we have to say R cross F or F cross R. Does it matter whether we put F first or R first? Yes, it matters. So if when you stretch your fingers along R, the first vector in the expression for the product. So if you say F cross R, F multiplied by R, that means you have to stretch your fingers along F first and curl it towards R. That will give you the wrong direction, the opposite direction to if you do otherwise. So it matters. Okay. Now, net torque. So you know the word what net mean? Sum of all the torques, right? So because we're going to need this net torque, like we said, net force, because the Newton's second law is the net force equal to mass into acceleration. So we are trying to get a corresponding Newton's second law for rotational motion. So whatever we have for force, whenever we have an equation where there is force, we have to replace the force by torque for rotational motion. So we need to find the net torque. So what is the net torque? Simply the sum of all the torques. Okay, this is the symbol for summing it up. So this means torque 1 plus torque 2 plus torque 3 and so on. If that is more than 3, you have to keep on adding. So we call it net torque. Now, like the forces, we have to be careful with the direction because they are vectors. We have to add as vectors. Here also, we have to add vectors. What the thing is, we will stick to one dimension here, meaning it is rotating, all these things is in one plane. So it will be the direction of the torque is either out of the plane or into the plane. So we have only two directions, positive direction, which is out of the plane, which is counterclockwise, and negative direction, which is clockwise. So either the torque will be positive or negative. Positive is when counterclockwise rotation or trying to turn it counterclockwise by the torque, or when it is trying to turn it clockwise, it is negative. So when you add, sometime the torque will cancel. Yeah. No, you have to, from the number, they will only, maybe in the question, he will only give you the magnitude. And you should figure out whether it is a positive torque or the negative torque. We will do exercises, okay, don't worry. So that is part of the thing that we will test you, whether you know how to get it positive or negative, right? Okay, let's see. Okay, here it is. So we got a question. Now we will see whether we understood it or not. Okay, whether we have understood how to get the direction. A board, okay, this is the board, pivoted at the left-hand side. So here it is pivoted, left-hand side. Three forces, F1, F2, and F3. You can see those three forces, right? This is F1, this guy, and this guy is F2, and this guy is F3. We have three forces acting on this board at different places, right? Now, where the force is applied matters. That is the main thing why we discussing this torque. Torque is not just a force. It has something to do with the force. Additionally, it has something to do with where the force is applied. Okay, so according to where the force is applied, the turning effect or the rotating effect will be different. Find the net torque acting on the board around the point. Which point? This point P. So the torque, we have to tell around which point. That is important. It is not only, if someone asks you, find the torque just like that, we cannot answer that question. You have to also find the torque about which point, around which point. So he is telling us to find the torque about the point P, the net torque. That means the torque from all three forces. So let's see how we do this. So the net torque is equal to torque 1 from the force 1, from the torque from force 2, and the torque from the force 3. So tau 1, tau 2, tau 3. So let's start with the force number 1. Okay, so it is magnitude is R1 F1 perpendicular. So you can say RF sine theta. That is one way of doing that. But you can also say R1, that is the distance of the force to where. So this will be the R1. Let me choose a different color. Okay, red. Red is going to be black. So this is R1, and this is your force, F1. So it will be R1 is equal to how much? 2. Because 4 meters altogether, half of that is 2. So 2 multiplied by the perpendicular component of perpendicular to R. So this is the perpendicular component of F1. If this angle is 60, making with the position vector R, so F1 perpendicular will be 12 sine 60. This is the magnitude. I'm taking the torque from the force number 1. This is just the magnitude. Now you have to take care of the sign also. You should put whether it is positive torque or the negative torque. Now how do we get it? This is how. This is the point in question, and this is the force we are applying. So this is the point in question. This is the force we are applying. And which direction that 12 Newton force is trying to rotate this board? Counterclockwise or clockwise? Clockwise. So it is negative, right? So clockwise turning effect, you put minus sign. Clockwise is negative. Okay. Counterclockwise turning effect will be positive. So here, imagine this is the only force. 12 Newton is the only force. And say it is pivoted at the point P. If that is the only force and it is pivoted at the point P, which direction this board will turn? It will turn clockwise, right? So the turning effect of the force F1 is negative, clockwise. So you put a negative sign. Now let me go to the next slide because it has been done there. So okay, go back. Fine. Now let us quickly, get the torque 2. Torque 2 will be 7 Newton. No, yeah, it is perpendicular already, right? This is the R now. This is the R2. F2 is already perpendicular to R2. So the angle is, it making with the x-axis 90 degrees. So the perpendicular component is the total force. The force is already perpendicular to R2. So sine 90 is equal to 1. So this force will be just, R is equal to 4 and the force is equal to 7. And sine 90, that is 1. Is it positive or negative? Positive. It is trying to rotate it, not because it is up. Okay. Now you have to be careful. Don't say it is positive because direction of the force is up. There may be instance where the direction of the force is up, but the torque can be negative. It's not from the up down. You have to look at what is trying to do, whether it is trying to rotate it clockwise or counterclockwise. If it is trying to rotate counterclockwise, it is positive. If it is trying to rotate clockwise, it is negative. So this is anyway positive. Now let me look at torque 3. Torque 3 is from the force F3. It will be, R will be 1 meter now. And the perpendicular force will be 10 sine 30, not 10, because it is at an angle. So the perpendicular component of 10 Newton will be 10 sine 30, because making an angle of 30 degrees with R3. This is the R3 now. R3 is equal to 1 meter and 10 sine 30 is it positive or negative? It's also positive. Okay. So fine. Now let's go to the next slide. So what he's doing is, I mean, he is collecting all the counterclockwise torque from F2 and F3. The torque is counterclockwise, and from F1 the torque is clockwise. Then you just calculate and get the answer. The net torque turned out to be positive. Although some of them are trying to turn it clockwise, some of them trying to turn it counterclockwise, but the counterclockwise torque is bigger than the sum of all the clockwise torque. So the net torque is positive. So eventually it will turn counterclockwise because the total torque is net torque is a counterclockwise torque. Yeah. Okay, let me, okay. Why the torque from number 1 is clockwise, right? Number 3 is counterclockwise. Okay, we want to compare these two guys. Okay, right. Okay, let me draw it here. Say this is the force. Let me look at the F1 first. F1 is like this, right? And it is pivoted here. We want to talk about the point P. Imagine F1 is the only force. It will turn clockwise. So the torque from F1 about the point P is clockwise. Okay, good. Now let's take this guy, F3. Imagine F3 is the only force. It's clear, right? But you have to be careful. It's not because it is up, it is positive. Say, for example, you want to talk about not the point P, but the point Q. Now, everything will be reversed. The torque from F3 will be clockwise, and the torque from F1 will be counterclockwise. Okay? All right, so in our joint, we have rotational motion, right? So usually we have, not usually, always it is the case, right? The muscles come in pairs. One muscle trying to rotate the thing about the joint clockwise, the other one will be rotating it counterclockwise. So that's why because you cannot push with the tendon, we can only pull. It's like a string or a rope. So you have to, they have to come in pairs. So I think the bicep here, this is the tricep here. So the bicep will, here it will trying to rotate counterclockwise, not, it will rotate counterclockwise rotation, and the tricep will do the clockwise rotation, depending on how you are looking at it for this figure. Since the tendons connecting the muscles to the bone are usually attached close to the joint, large forces are needed to achieve locomotion or equilibrium. What he means is, see, this is the joint, right? The pivot point. And this is the tendon. The tendon is very close to the joint. So the torque will be small, because torque is equal to the force multiplied by the distance to the joint, right? Because the distance is small, the torque is small. It is like trying to open a door. Imagine you, instead of by mistake, without putting the handle here, this is the hinge. If you put the handle here, it will be difficult to open the door, right? Right. So, but this is what is happening here. The tendon is connected very close to the joint. That means the muscles have to exert extra force to rotate it. So since the tendons connecting the muscles to the bone are usually attached close to the joint, large forces are needed to achieve locomotion or equilibrium. These large forces are of interest in kinesiology. In medicine, probably you will learn later another branch called kinesiology in medicine because joints have, I'm sorry. No. Kina mean motion, kinetic, not energy, motion. Okay, so things to do with motion, sports medicine, and so on. You have this kinesiology. And medicine, because joints have relatively high likelihood of failure during their lifetime, not only as a result of injury, also as a result of degeneration, like arthritis and so on. Okay, now we are going to do some equilibrium problem again, but this time not for a point object, okay, but now you can break equilibrium because of rotation as well. So we have to bring in, to say that net force is equal to 0 is not enough for equilibrium. You saw that, right? Because suppose you keep something on a horizontal table and you apply a force 10 Newton like that and another 10 Newton like that, the net force is 0. But is it in equilibrium? No, because the forces are not concurrent. So there will be a rotating effect. There will be a net torque. Okay, if you take this point, for example, say point here, the torque from this guy will be say 1 meter, so 10 Newton meter, but it is minus. Trying to rotate it, plus from this guy. Okay, this is plus. So let me use different colors now. And from this guy, also, this guy also plus. Both of them about the point P. Say it is pivoted here. Both these forces have a positive torque, right? The 10 Newton, let me use different colors so I can. Okay, let me put this guy in red. And this guy in blue. Both are 10 Newton and say this is 1 meter distance to the pivot point. The blue 10 Newton is trying to rotate it counterclockwise. The red 10 Newton is also trying to rotate it counterclockwise. They are not going to cancel. So the net torque is 20 Newton meter because 10 plus 10. So although the net force is 0, the net torque is not 0. So for a complete equilibrium, called mechanical equilibrium, this is not enough. We need one more condition. Net torque also has to be 0. Then it will be in equilibrium. For a rigid body to be in equilibrium, 2 conditions must be true. So we call this translational equilibrium, this guy, and this is the rotational equilibrium. Right, now we have got some question. The next slide shows 5 locations of fulcrum along a red bar upon which fulcrum is the joint, okay, around which it can turn. 5 forces of any magnitude act. Which of the 5 cases cannot be in rotational equilibrium? So we have 5 cases, A, B, C, D, E. It is the case A, fulcrum is here for this, and we have 1, 2, 3, 4, 5 forces acting. all of them 5 forces acting. And these forces, we can change the magnitude. Okay, we can make it small or big, but not zero. Okay, not zero. You can make the size to be any value, but you are not allowed to change the direction. And you are not allowed to change where it is applied. You can only change the size of the force. Now the question is, which one of these 5 configurations we cannot have rotational equilibrium? Okay, I don't know. Okay, shall we go one by one? Okay, right. Okay. So this is A. Let me start with A. Now, if you have to have rotational equilibrium, we need to have counterclockwise torque as well as clockwise torque. And we can adjust the size of the counterclockwise and clockwise to make it equilibrium. If suppose we have 10 plus 10 torque, we can make the other one minus 10, the net torque from the clockwise minus 10, make it equal by changing the size of the forces. We can bring it to equilibrium. So the only requirement is we need to have at least one counterclockwise and one clockwise. If all of them are counterclockwise, we cannot have rotational equilibrium. If all of them are counterclockwise also, we cannot have rotational equilibrium. Now we can answer the question, right? Okay. People online, did you understand this? I'm going to give a question like this in the exam. Okay, right. All right, let's go. Not sure. Okay, let me repeat it. Nura, now I got your attention. Okay, right. So now, you know, if something is to be in equilibrium, the net torque has to be 0. Okay, so you can group all the counterclockwise torque and group all the clockwise torque. If all the torques are counterclockwise, we cannot bring it in equilibrium because everything is positive. We don't have any minus torque to make it balance it. Or if all the torques are clockwise, again problem. That's why you have to have at least one counterclockwise and one clockwise. Okay. Is it clear now, Noora? Yes. Okay. Right. So let's look at this. Now I'm going to number them 1, 2, 3, 4, 5. So we have 5 torques from each of these 5 forces. Let's start with number 1. Is it clockwise or counterclockwise? Imagine 1 is the only force, and this is the fulcrum. Always look at where the fulcrum, where the point, the torque, where it is pivoted. Counterclockwise, right? If that is the only force, the 1 will turn it counterclockwise. So 1 is positive. Good. Number 2, also positive. Number 3, nothing. Very good. Why? Because theta is equal to 0. The angle between R, it is parallel. There is no perpendicular component. The force is parallel to R. That means theta equal to 0. That means sine 0 is 0, the torque is 0. The torque from 3 is 0. So okay, we got 1 is positive, 2 is positive, 3 is 0. Okay, we cannot do anything with him. Okay, what about number 4? Number 4 is clockwise. Yeah, clockwise, right? Okay, that's it. We have at least one counterclockwise and one clockwise. So we can adjust the size of the forces to make, bring it to 0. So this is possible. A, it is possible to make it equilibrium. Okay, that is not the choice. Okay, B. Let me delete what we have. Okay, let me do the same thing again. 1, 2, 3, 4, 5. Okay, let's start with number 1. 1 is counterclockwise positive. 2 is positive, 3 is 0, 4 is clockwise, negative. That's it. Okay, we are happy. Okay, what about 5? Now we change the fulcrum. For in this, the fulcrum is here. So number 5, now tell me, is it positive or negative? Talk 5, positive. Here, nothing. Oh yeah, number 5 here is 0, right? Why number 5 is 0? Is it because r equal to 0, f equal to 0, sine theta equal to 0? R is equal to 0. It is okay, but here 5 is okay, fine. So do we have one positive and one negative at least? Yeah. So B is also possible. Make it equilibrium. Yeah. Now let's go to C. Okay. 1, 2, 3, 4, 5. This is the fulcrum. 1 is 0. Why? The reason is R equal to 0. Because the R is 0. The point of application of the force and where you want the torque is coincident. Okay, in the same place. So that 1 is 0. 2 is positive. 3 is 0 because theta equal to 0, not R equal to 0. So we have 1 positive and 3 zeros. 4 is also 0. 5 is positive. We don't have any negative, right? So this is the one we cannot bring it to rotational equilibrium. So this is, I mean, no rotational, cannot have rotational equilibrium. This is the correct pick, one of the choices, right? The question is, what is the question? Which one of the 5 cases cannot be in rotation? So C cannot be in equilibrium, okay? Cannot be in rotational equilibrium. So let's go to D. All of them, yeah, positive, 0, negative. Okay, this can be in equilibrium. What about this? This is 0, this is 0. This is, okay, let me label it. 1, 2, 3, 4, 5. The fulcrum is here. 1 is negative. 1 is negative, right? Clockwise. 1 is negative, 2 is 0, 3 is 0, 4 is positive. So only choice is C. Okay, right. Good. So now we have a question from physiology. We have a foot of a man. You call standard man mean the standard man has a standard weight and so on, mass and so on. So the mass is 70 kilograms. Standing on a flat surface, calculate the magnitude of the 2 normal forces supporting the foot. So it is touching the floor in 2 places. Okay, we approximately say, okay, at this point A and this point C. So at the point A, there is a normal force from the floor on the foot. Say we'll call it N1, and at the point C, let me call it N2. Okay, we have to find the N1 and N2. Assume the Achilles tendon is relaxed. So this muscles here is called the Achilles tendon. It is relaxed. Okay, relaxed means tension is 0. So we say it is relaxed. So no force from there. The force due to the upper body pushing into the foot. So whatever above his body pushing into the foot, that force we call it in the foot half mg. This will be half of the weight. Now, is it reasonable to say that? Because you're only looking at 1 foot. So if you are symmetric, half of my weight will be on the right foot and half of my weight will be on the left foot. So it's a reasonable assumption. Okay. Now, we have given this value and this value. They are not equal. X1 is equal to 6.2 and X2 is equal to greater, 12.3. So that means N1 is going to be different from N2, because it is not in the middle. The mg, half mg from his weight is not going to be equally distributed at this contact and this contact. So we are supposed to find this N1 and N2. So let's first find half mg. His weight is 70 kilogram. His mass is 70 kilogram. Weight will be 70 multiplied by 9.8, divide by 2. So the force on the that left foot or right foot. Okay, it is right foot. Doesn't matter. Okay, fine. It is right foot, right? Never mind. Doesn't matter. It is asymmetric. Yeah. Why the magnitude is divided by 2? Yeah, because we are only looking at one side of the body. Okay, 1 foot on 1 foot, because we have 2 feet, right? So so the weight will be half of the weight on right foot and half of the weight on the left foot. So that's why I divide by 2. Now, this 343, I mean, suppose the weight is exactly in the middle, half of 343 will be at for N1 and half of will become N2, because it will be equally distributed, but it's not the case. Your weight will be, on the foot. It is give. This is some from experiment or whatever. The x1 is equal to 6.2, and this is equal to 12.3. So your heel is going to get more pressure than your. That is a fact, right? More than from the other touching the fingers or toes touching the ground. So how do I get the exact value? Well, I can apply, and he is in equilibrium. So I can apply the net force is equal to 0. So the net force, there are only 3 forces acting on the foot. N1, N2, they are both positive. And the half of the weight, which is the force external to that foot, okay, from the rest of the body, weight from the rest of the body, half of the weight, that is negative because it is down. So we have this equation. From this equation, of course, the N1 plus N2 must be equal to half of the weight. Okay, that's fine. But can I find exactly what is N1 and N2? It is not half of, this is not going to be distributed half N1 and N2 because of the weight not being in the middle. You can find which? How do you find N1? Other equilibrium condition, yeah. So we have another equation for equilibrium, not only one. So although we have 2 unknowns, N1 and N2, but we have another equation. So we can have 2 equations, 2 unknowns. Fine, that's one. So what is the other equation? The net torque equal to 0, rotational equilibrium. Now he's not rotating also, so I can get this equation also. Now here, the net torque equal to 0 about a point X, because when you say find the torque, you have to specify about which point, right? So you can choose that this net torque equal to 0, we can take that point to be any point. Now it is not rotating about anything, okay? You can, if you want, it has to be rotational equilibrium. The net torque has to be 0 about the point A. It has to be equal to 0 about the point B. It has to be equal to 0 about the point C or any other point. Doesn't matter. It doesn't have to be on the foot. Okay, the B is not on the foot, right? It is somewhere here. So you can choose any point you like. And it has to be valid, okay? If it is in rotational equilibrium, the net torque has to be 0, no matter what point you take. It has to be valid for any point. So we have to be clever and choose a point such that I can answer the question quickly. Yeah. So here we are taking the B, point B, okay. Well, if let's follow what he has done. Okay, so I want to take the net torque about the point B and say it is equal to 0. So torque from N1, torque from F, torque from N2. So because we have only 3 forces acting on it, so each force will have its own torque. So torque from N1 will be this is N1 like that. This distance is x1, N1. Is it positive or negative about the point B? Trying to rotate it clockwise, right? This is the pivot point, and N1 is trying to rotate it about the point B, okay, about the point B, not any other point. It's trying to rotate it clockwise, so it is negative. What about the torque from F? That force is going through the point B. If the force goes through the point B, the torque will be 0 because the angle is 180. Let me show it. Okay, let me clear all the writings. See, this is F, right? And R will be, let me take another color. Okay, red maybe. So this is where the force is applied, and R will be this. R is the red and blue is the F. What is the angle between R and F? 180. And sine 180 is equal to 0. Sine 0 is also 0. So whether it is parallel or anti-parallel, the torque will be 0. So the torque from this is 0. Now the torque from N2 will be N2 multiplied by X2. Now what is the direction it is trying to turn about point B? Counterclockwise, so that is positive. So you get this equation from okay, right. Now we have 2 equations. One equation is this, and another independent equation that. We have 2 unknowns also. N1 is an unknown, N2 is also unknown. So basically we can solve it. Okay, I will not go through the solution. Okay, so this can be solved for both N1 and N2. Okay, but yeah, I will leave it. There will be other question where I will completely solve it, but I'm not going to finish it now. Okay, is there a question? Can you explain again why answer is C? Oh, Ahmed. Okay, you mean this one, right? Okay, I will do that. Okay, but how come you didn't follow it? Okay, right. So Ahmed, you have to interact with me. Ahmed, can you use the mic? All right. Oops. Are you calling me? Okay, I'm going to explain. Ahmed, please listen. The condition for rotational equilibrium is net torque equal to 0. Okay, fine. The net torque will be 0, can be made to 0 if you have at least one counterclockwise or one positive torque and at least one clockwise or negative torque. Did you get it? Say yes or no. Yeah, we have the freedom to change the size of the torque, okay? But we cannot change the position where the force is applied. R cannot be changed. The magnitude of F can be changed. And the theta cannot be changed. Only the magnitude of F. So our restriction is, our freedom is to change the size of the torque, okay? Right. Now, let me take A, then I will go to C, okay? Let me take A first. In A, the fulcrum is here. This is where we need the torque. And I'm going to call it number 1, number 2, number 3, number 4, and number 5. What is the torque due to number 1? Ahmed. I mean the sign, okay, not the magnitude. Is it positive torque or negative torque from number 1, force number 1? The torque from force number 1, is it positive or negative about the point P?
It's positive.
Positive, good. Number 2?
Also positive.
Very good. Number 3?
I think 0.
Very good. Number 4?
4 is negative.
Very good. See, we have at least 1 positive and 1 negative. At least. Okay.
Yes.
That means by adjusting the sizes, I can make them to be 0, the net torque to be 0. Yes?
Yes.
Got it. Now let me go direct to C. Okay. Now the fulcrum has moved. Okay. We have the same forces with the size can be adjusted. Okay. Let me start in number 1. What is the torque from number 1 about the point P? Now P is different place. Fulcrum. I'm waiting. Ahmed.
It's not move.
0. Okay.
Yes.
Can you tell me why it is 0? Is it R0, F0, or sine theta 0?
Because in the position point.
Yeah, which is 0 there, because you know the magnitude of the torque is RF sine theta. Is it because R equal to 0? Is it because F equal to 0? Or is it because sine theta equal to 0?
No, just because the position when he's doing the force.
What is position? Position vector is R, because R equal to 0.
Okay, R equal to 0, right.
You know, I mean, you forgot what R means. R is the position vector drawn from the pivot point, the point in question where you want to take the torque to where the force is applied. They are in the same place. So R equal to 0. That's why the torque is equal to 0. Okay, right. Number 2, positive or negative?
Positive.
Okay. Number 3?
0.
Why?
Because the angle
theta equal to 0. So sine theta
yes.
is parallel. There is no perpendicular component. Very good. Number 4?
0.
Okay. For reason?
Because the R is 0.
Very good. Number 5? Positive or negative or 0?
I think positive.
Okay. Think. What do you think? You should know to be positive. Imagine 5 is the only force and the rod is pivoted around that fulcrum point. Which direction will it turn? Counterclockwise. So it is positive, right? So do we have any negative torque here?
No.
So can you make it in equilibrium?
No.
No. We need to have at least one counterclockwise and at least one clockwise. We have the freedom to change the. Now it's clear, right?
Yeah, now it's clear. Thank you.
Right. Well, which one? A. We have at least one counterclockwise and one. Yes. Number 5 is because R is equal to 0. Number 3 because theta is equal to 0. Okay. Let's go to probably the last section in this about levers and physiological application. We have in the human body lever systems, right? It's like if you want to, lift very heavy thing, I can do with a small force by making the lever arm or the moment arm, okay, making the R of the torque big. So even though the force is small, the torque is big, right? Say, imagine this one is 1,000 kilograms, okay? And say this is 1 meter. And I am weak person, I can apply only 10 Newton. But this is 100 meters. So this torque from my 10 Newton is 1,000. And the weight torque is also 1,000. So I can lift it. It is balanced now. So, okay, so we have this, we call this lever system, okay, because we balance the thing by applying equal torque. So this is the fulcrum where it is rotating. Point, that is the fulcrum, it is called the fulcrum. The load is the one that we are trying to lift. It matters, but I didn't bother, you know why? Still it is equal, right? You have to multiply by 9.8 on both. So it matters, but I just ignored it because I just want to, yeah, okay, let's say 1,000 Newton. Yeah, I should have, sorry about that. Okay, let's say, oops. Oh, I put 10 Newton, I put 1,000 kilograms. That is wrong. Yes, thank you, Manal. Yeah, I thought they are both kilogram. Oh, sorry. It matters. I made a mistake. So that has to be both Newton. Right. Okay, very good. Now, we have different levels. We call these levels in 3 types. When the fulcrum is in the middle and the load and the effort either side, it is called the class 1. So example of class 1 lever in the human body is the skull. Okay, the skull, the whole thing, you know better than me, right? It is supported, the whole skull is supported here. From the spine, I think. They have names. Tell me. Between the points at which the weight, the spine, it actually is like that. It is the whole skull is supported on the spine. So now we have a muscle, this is the trapezium muscles or something, and the weight of the skull is front. Okay, so if the muscle is relaxed, okay, if your trapezium muscle, something, come on guys, you did PHS, okay, trapezium or something, it is in the next slide, okay? So suppose you are in my class and you get bored, you sleep, right? This muscle relax, what will happen? You go like that, right? You will fall because the muscles is not supporting your skull weight. So you will fall down. I mean, your head will drop down. Yeah, the name is not there. Maybe the next time muscle. Yeah, this muscle, you can draw it like this. This is the skull weight, mg, and the muscle force this. If this muscle force becomes 0, like when you relax, when you go to sleep, it relaxes, then your head drops. Okay, if you doze off. Okay, now class 2. So class 1 is what? You have to say what is in the middle. If the support or the fulcrum is in the middle, it doesn't matter which side is the effort and which side is the load. It doesn't matter. It is about who is in the middle. If the fulcrum is in the middle, it is class 1. So example of class 1 lever in the body is the skull. Okay. Yeah, we are looking at the skull. The spinal cord is supporting. I mean, The skull is the one we are looking at. It is supported at the spinal cord. Okay, so this is the weight is here, and this is the muscle, the tension. So support is in the middle. Okay, that is class 1. Class 2 is load is in the middle. Okay, class 2 is like you can have the support here, and the load is in the middle, and the effort and the fulcrum is either side. It doesn't matter which side, left or right, and which one is left, which one is right. It's not immaterial. Okay, you only have to look what is in the middle of the three: fulcrum, load, effort. The example in the human body for class 2 level is when someone is tipping on his toes. When you tip on the toes, this is the fulcrum. The support is the flow, right? The foot tipping. And the weight is the load. And Achilles tendon is the effort. So there's an example of class 2 level in, glad you found it interesting. Okay, that is in class 2 example in the human body. Now, what is this? Class 3. So what is class 3? Effort, the third one, the effort is in the middle. Example is the forearm. Okay, yeah, the forearm, okay, forearm. Here, see, the fulcrum is in the middle. Not middle, sorry. The fulcrum is here, joint. Joint is the fulcrum, sorry. Okay? Joint is the fulcrum. What is in the middle is effort. The muscle. So it is this direction. The muscle force is like that. And the weight of the arm, okay, is on the other side. And the fulcrum is one side. This is class 3, okay, tendons. Okay, the direction is not shown correctly. I don't know why it is drawn like that. I will correct it maybe later. Direction of the force, well, he's showing the perpendicular force. This is the tendon, right? So the direction of the force. Direction doesn't matter, it is in the middle. Okay, that's all. So we have the effort in the middle for class 3. So for each of these different classes, we have examples in the human body. Okay, I think I have to stop. I think we have classes at 9. All right, okay, see you in the next class. Okay, Abdullah, Manal, Judy. Okay, thank you.
Thank you, Mr.
Thank you, welcome. So